Okay, so welcome back. Gonna flash on the screen here the list of 17th century mathematicians outside of France that we had began discussing. So we mentioned Cavalieri is really the first to advance past Archimedes in computing areas under curves, and so he came up with Cavalieri's formula, which is technically uh, the power rule for integration, right? This is like the first integral that's computed, basically. John Wallis extended that result. Mercator also, so John Wallis extended that result to a general polynomial, so finding the area under a general polynomial. Mercator took care of or one of the cases, finding this power series expansion for natural log that's shifted. And we ended with a discussion of Huygens. So as I mentioned last time, Huygens had he's probably most famous for his contribution to optics, which is the wave theory of light. In optics, he's responsible for the wave theory of light. Probably his most famous contribution. He also studied the rings of Saturn. So astronomically, he had a few achievements to his name as well. He, to a lesser extent, he studied basic probability and used expected value. And this would eventually be expanded. So Huygens' work, together with Pascal's and Fermat's earlier work, would be expanded by one of the Bernoullis. I believe it's Jacob Bernoulli, but I could be wrong. With the Bernoullis, it's always hard to keep track because there's so many. There's a ton of them. Jacob and Johann are the kind of the first two, and they're contemporaries of these 17th century mathematicians we've been talking about. And so there were some later Bernoullis in the mid 1700s that did some further things, but it can be hard to keep track of of which did what, because there's a ridiculous amount of them that contributed in some way to math. So, but anyway, one of the Bernoullis expanded that to basically be like the foundations of the theory of probability. As I mentioned last time, Huygens also introduced the study, or I should say introduced, but he was one of the first to seriously study cycloid. So what is a cycloid? A cycloid is another example. So we now have several examples in this course of these kinematic curves. So these are curves defined by some kind of motion. There's a number of ways that you can think of defining a cycloid. Imagine you have, say, a surface, right? This is like the floor, okay? And on that floor, you take a circular ball. We're viewing it from the side here, okay? And let's say you mark, say, a point on that circular ball, okay? We'll just mark this point, the bottom, okay? And imagine that you've, marked this point in such a way that when you push this circular ball in that direction, you're rolling it, okay, along the floor here, you're going to keep track of what path that point traces out as this circle rolls along. What trajectory would it have? So if you look up like at the wiki article of cycloid, you can see some nice animations here. And so if I were to do that, it can be hard to see it from a stationary picture, but if I were to do that, the path that gets traced out looks kind of like this. And of course, this is once it's back to its initial position. This is it rolling once, basically. And then when it rolls again, here's another arc. Now, you might look at this thing and be tempted to call it some kind of semicircular thing or semi-elliptical thing, but it's not. Okay, it's not an arc of an ellipse. It's not an arc of a circle. A curve that looks like this or is a piece of this is called a cycloid. So this is what a cycloid is. Okay. You can also do the similar definition upside down. So you could roll this, you could say that it's magnetic. You've attached it to the ceiling and you're rolling it in the other way. So it doesn't have to be shaped exactly like this. This is another example of a cycloid. Okay, something like that is another example of a cycloid. And so, say if I took just that piece and considered that piece, that is just an arc of a cycloid or part of a cycloid. Okay. Now, why would I focus on the study of cycloids? So there's a very interesting thing here that Huygens didn't quite realize it at the time, but this comes into a very interesting question, and this question was originally posed by Johann Bernoulli. So this is so Johann Bernoulli in 1696 posed what is called the Brastochrone problem. Okay. So Brastochrone means shortest path. So this is shortest, or sorry, I should say this is shortest time. That's what this means. So shortest time, or least time, I should say here. So this is shortest time problem. I think I have the quote of the original statement. So the original statement, problem statement, this was addressed to all European mathematicians. So addressed to all of Europe's leading mathematicians, which, as I said, included Johann's brother, Jacob. So the problem statement is this: I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will bestow fame and remain as a lasting monument. Following the example set by Pascal, Fermat, etc. So see, notice Johann Bernoulli already crediting Pascal and Fermat with a lot of work. So following the example set by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will test their methods and strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. And so here is the problem statement. Given 2 points, A and B, in a vertical plane, what is the curve traced out by a point acted on only by gravity, which starts at A and reaches B in the shortest time? This has to be slightly amended so that A and B are not directly below each, or A and B are not directly vertical. So the Brastochrone problem So the Brastochrone problem is given points A and B in a plane, A and B not directly below each other. What is the curve traced out by a point with gravity the only acting force. Which means, i.e., what is the shortest or least time path between the 2 points. This is the Brastochrone problem. Okay. Now, Johann had probably already solved this before he posed the question to make sure that he didn't make himself look bad. So he had probably figured this out before he posed this as a challenge. His brother would submit a solution that would be almost the same as his. So they came to almost the exact same solution. Newton got this letter. So Newton received this letter at, I believe we even have the time, at 4 p.m. The 29th of January, 1697. Okay, when he got home. Okay, so he found this letter. That was the challenge that I read out. This is a letter directly from Johann Bernoulli. Newton stayed up all night to solve this. So Newton stayed up all night to solve it. He was really annoyed by the problem, but after some hours, 12-ish hours or so, he worked it out. Now, supposedly, he sent this letter, or his solution, to Bernoulli, and his solution read essentially this. Here was Newton's solution. It was like some scribbles, like maybe a little bit of math worked out, and then it is a cycloid. Okay. So apparently Newton's letter was extremely short and had almost no work on it, had a little bit of scribbled stuff written, and then the words, it's a cycloid, which is correct. So the answer to this is an arc of a cycloid. So if you don't believe that an arc of a cycloid is the shortest path, or the path of least time under this setup, I recommend that you watch the animation on the wiki article for the Brastochrone curve. So if you've seen the Tautochrone curve, you'll realize that, oh, that's also a cycloid. So if you have a look at that animation, it illustrates, there's a very nice animation like right at the top of the page on the wiki that shows an actual animation of objects acted on only by gravity falling along certain paths, and it shows how the cycloid path is the fastest, or the path of least time. So anyway, so Newton was correct. He did a little bit of scribbling and work. That's like all he included in his letter. Apparently, it was really, really short, and it just said it is a cycloid. And supposedly, Johann Bernoulli, when he got this letter, this response from Newton, it didn't say Newton's name or anything. Okay, so the letter didn't include Newton's name. It said literally nothing about who sent it, so he didn't know who the letter was from. So he gets a letter, and it just has some scribbling, and it's a cycloid. And Johann Bernoulli said, like, I can recognize a lion by its paw. And so he knew it was Newton, even though Newton didn't include anything to indicate that it was him. So he could tell by just by the way that Newton had written this furiously and in anger, but he could tell by the strength of his computations that it was Newton. So that's the story. So Newton apparently wrote that He doesn't like to be, he said, I do not love to be pestered and teased by foreigners about mathematical things. Was his response to it. But nevertheless, I guess he found it interesting enough that he had to immediately stay up all night doing it. So this is the first question in a subject called the calculus of variations. So this is the first question. This is the first problem, I should say, in a field known as the calculus of variations, which is a very, very interesting field that is... what's cool about the calculus of variations is the problems themselves can be stated very simply, and a lot of the problems come directly from physics. They can be stated very simply. So just some basic questions about pendulum, like a pendulum or a double pendulum even. Some basic questions about that can actually be really, really hard to work out. So I should also mention that I believe Huygens is also known for his work in the creation and study of the pendulum. So it's not that surprising that he happened upon some of these things, since those sorts of considerations are important in this field. So anyway, yeah, this is the first known example of a problem in the calculus of variations. If you ever take a course on calculus of variations, the Brastochrone problem will probably be literally page 1 of any textbook. Is this problem? Okay. So, but this also kind of gives you a preview of Newton's ability to compute, since supposedly it took Johann Bernoulli a couple weeks to do it. Okay, so let me see here. So Isaac Barrow, his most important contribution was he resigned his professorship so that Newton could take over. So when it comes to academia, it is a common issue. It is a common issue that older faculty don't retire, until they're well advanced in years, and so a young aspiring mathematician might encounter a wall, especially hundreds of years ago when maybe there weren't that many of these positions here at Cambridge, and so Isaac Barrow actually recognized how strong of an addition Newton would be, and resigned his professorship. So that's pretty cool. So Gregory, just before we start talking about Newton and Leibniz for probably most of the rest of the lecture, Gregory used the earlier results of Wallace to obtain what's called Gregory Series, which you may have seen before in Calc 2. This is the identity that x is tan x minus 1/3 tan cubed x plus 1/5 tan to the 5th x minus, and so on. Okay, like this. So you might notice that if you put x equal to pi over 4, okay, so that tan of x is 1, then what you get here is the identity pi over 4 is 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9, and so on. Now, this is not a great series to use to approximate pi, so you'll sometimes, right, you could multiply both sides by 4 to say that pi is 4 minus 4/3 thirds plus 4/5. If you're not comfortable with that, that's fine. But using this to estimate pi over 4 or pi is not that great because this is a very slowly converging series, but nevertheless it's kind of an interesting fact that this works out in this way. This had also been obtained by an Indian mathematician around 1530. So this series had been obtained by an Indian mathematician in approximately 1530. Okay. All right. At least this tan series, a form of this tan series, had been obtained in this way. Okay. So now I had already mentioned Johann Bernoulli. That's pretty much all I wanted to bring up, was the fact that Bernoulli had posed this Brastochrone problem. There's a lot that both Johann and his brother Jacob did, so I'm not going to get into that. Also, I can toss into that basically all of the mathematical accomplishments of the entire Bernoulli family. So if you're interested in that, you should look up the Bernoulli family, and you can view the individual entries in the list. So Johann and Jacob were the first. And kind of the one thing that didn't get mentioned was their contributions to early probability theory. Okay, so Newton. Of course, Newton is probably most well known for his contribution to physics, right? The name Newtonian mechanics. This was basically the physics world model prior to relativity and quantum mechanics in the early 1900s. And so, Newtonian physics, you've no doubt heard, is the era of physics post-Newton after his Principia Mathematica. And so I'll get into the specifics of that, but it's impossible to hear the name Newton and not think that. So Newton's life was, so some of the things that you probably know the most about Newton is maybe his life after he arrived at Cambridge, but just kind of a brief summary. So Newton never knew his father because his father had died before he was born. He was originally supposed to learn farming, but instead he spent all of his time doing experiments and building mechanical models. So eventually, because of his nature, his uncle sent him to Cambridge, and there's when he read Euclid, Descartes, Kepler, Wallace, and he attended the lectures of Isaac Barrow, who would eventually, as I mentioned earlier, give up his professorship to Newton. So by the time he got his BA, Newton had discovered derivatives, which he called fluxions. So he discovered, and I'm going to put a co here, but he discovered them independently. So he discovered fluxions, which we now call derivatives. Okay, so when you take a calculus class, right, you are not doing calculus until you're doing derivatives. Right? Derivatives and integrals are the things that define whether or not what you're doing is calculus. Okay, so he co-discovered calculus for this reason. He would also later describe, much later, he would describe fluents. So later he would co-discover fluents. So the co is just who gets credit. I'm not saying that he collaborated with anybody. He did this independently. So he co-discovered fluents, which we call integrals. Now, again, I should say technically the word discover here might be a little bit disputed because, as I mentioned, Cavalieri was able to compute an integral of x to the n, right, for all powers, all integer powers of n except -1. And before him, right, Archimedes was able to compute, technically was computing an integral, a definite integral in a way, of a degree 2 term. But Archimedes is he was very close to what would eventually become integral calculus, but Cavalieri is the first to be doing like the immediate precursor to this thing. But Newton described fluence more generally than just in those specific special cases. Okay. All right. And so the reason for this addition of co here is because while he did this, he didn't publish his results until later. And by the time he published his results, someone else had already published, and that someone else is Leibniz. Okay, so the reason for this co is Leibniz, which I will defer to talking more about until later. So, in fact, in our textbook here, Leibniz gets his own chapter. Newton gets tossed in with the other 17th century mathematicians, and Leibniz gets his own chapter. So I guess we know where the allegiances of the authors of the textbook lie. They're definitely Leibniz respecters. They're not Newton fans. Or at least when it comes to his contribution to math. Newton proved the binomial theorem, or I should say Newton had deduced the binomial theorem. So remember, Pascal had shown an earlier version of this, but he had deduced the binomial theorem for fractional exponents. So he had deduced the binomial theorem for integer and fractional exponents. Though without completely rigorous proof. So he used this binomial theorem to expand functions into power series. So he used the binomial theorem to expand functions into power series, which we've mentioned previously with Wallace and Mercator, specifically with Mercator. Okay. So when he wanted to compute the area under such a function, or under the graph of such a function, he would combine this power series expansion with Wallace's method to do this term by term. All right. So the idea is you expand a function into a power series. This is kind of like an infinite polynomial. Okay, and then you would apply Wallace's method. So what he was doing here, even though we call them Taylor series, and we'll talk about the person they're named after in the next chapter, but even though we call them Taylor series, Newton was working with essentially these Taylor series already when he was doing this. So when he wanted to compute the area under a graph, he would use Wallace's method to do this term by term to be able to compute this. He was essentially integrating term by term when he was doing this. And so the thing is you might recall from your Calc 2 days, when you are dealing with a power series, right, this is an infinite sum, right? And power series, even the ones that are very tricky, can be very, sorry, even the ones that are very simple can be very tricky. So for instance, if we have the power series that is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. Sorry, so this is not a power series. This is just a series. So, but power series are more general things because I can plug numbers into power series. So this would be a particular value of some very simple power series. So here's a sum, right? So I'm not calling this a power series. Maybe I should get rid of this arrow. And here's another sum. Okay. And as you might recall, this doesn't sum to anything. This is infinite. This diverges. Okay, so this, you sum up all this stuff, it's too big. It just keeps getting bigger and bigger and bigger. It goes off to infinity. But this sums to a finite number. So this is not infinite, right? And just looking at them, it becomes hard to actually see what it is that's going on here, right? So just looking at these things, you can't really tell just by glancing at them. Okay, but as it turned out, at this time, they weren't terribly worried about convergence of these power series, so convergence questions were ignored. So convergence questions were ignored here, and because of that, they were willing to do operations with power series that we would consider dubious today. Now, it happened that many of the things they were doing turned out to be valid. They just didn't. They basically just got lucky in the sense that their reasoning wasn't really backing them up. But it turned out that a lot of the things they were doing were valid, but they didn't realize that there could be a problem there. Okay, so I'll talk a little bit more about that later, depending on the direction we go in, kind of after we get out of 17th century math. Okay, so during the plague of 1665 to 1666, Newton actually went back to his family farmhouse, and that is where he thought about gravitation. And he took over Isaac Barrow's professorship in 1669. So in 1669 he became so he takes over Barrow's professorship. And around this time is when he discovered the decomposition of white light by a prism. So discovered decomposition of white light via prism around this time. Okay. So from 1673 to 1683, he lectured on algebra and theory of equations. Okay, some of his work from this time led to things like Newton's method. If you remember Newton's method from Calc 1, that comes from this period. So Newton's big thing, his absolute like crowning achievement, is Newton's theory of gravitation. Okay, so F equals ma, or written out. Right. Okay. So his description of law of gravitation, right, is actually still valid today. It needs to be slightly modified because there are slight differences with the theory of relativity, but this is within epsilon. This is like current physical knowledge, right? So has to be slightly modified. But the idea is if big M is the mass of the Earth, assumed to be concentrated at its center, and little m is the mass of, say, the apple on or near the surface, okay, then this quantity, which writing in Newton's notation, I'll talk a little bit about that later, writes this as acceleration. So if you've taken, a lot of times in differential equations, you'll see this notation used for the second derivative instead. So this was the acceleration term. Then in that instance, or in that setting that I just mentioned, so if big M is say the mass of the Earth, it's soon to be concentrated at its center, and little m is the mass of an apple on or near the surface, then this acceleration term is almost constant. So in Newton's theory it was constant, but but it's almost constant basically. And this also confirms Galileo's observations, right? So this confirms Galileo's observations. Okay. So the thing that came out of Newton's big work, so Newton's magnum opus is Principia Mathematica. Okay. And it is in Principia Mathematica that he lays out all of these things, his gravitational theory. And the big thing was he deduces Kepler's laws of planetary motion from his theory of gravitation. So this is his crowning achievement and the reason why he is forever known, as this is huge, right? So finally, all of the previous astronomical work that I laid out of all the astronomers leading up to Kepler kind of having the best idea of what was going on, this gets finally smoothed out entirely by Newton. To a point that it would not really be improved upon, at least in an overall sense, until general relativity in the early 1900s. Now, there's a thing, right? So Newton worked through his arguments in Principia Mathematica using these fluxions, right? So he worked through Principia Mathematica using derivatives, and when you are talking about derivatives, as you might recall, the notion of an infinitesimal comes up. And Newton himself was probably not worried about problems with infinitesimals because it seemed like mathematicians weren't too terribly worried about it until much later. So Newton probably himself didn't think that infinitesimals were sketchy or bad, but he worried, I think, that his peers would not believe the computations that were done using basically, the differential calculus that he had discovered. And so rather than use those arguments, he used Euclidean-style geometric arguments for all of these things, which he was able to do, but those arguments are way more convoluted and complicated, and because of that, it is very hard to read Principia Mathematica today. So I had earlier mentioned this compilation book. It was called On the Shoulders of Giants, and it had works by Copernicus, Galileo, Kepler, Newton, and I think it even has Einstein's first paper on special relativity. Principia Mathematica is included in that compilation. I believe it's the longest work of everything that's included, and it is really, really, really hard to go through and understand exactly what's happening. So very hard to read. Now, on account of that, but he did this probably because he knew that no one would raise a fuss, since that was the kind of argumentation that they were used to. So no infinitesimals. And so he published Principia Mathematica. This was 1686. Was when this was published. It was published in 2 volumes. The second volume of Principia dealt with hydrostatics and hydrodynamics, and the biggest takeaway from this was that Descartes' theory of vortices didn't work. And so soon after, Newton's theories were accepted everywhere, and this was the beginning of Newton's very strong influence on physics. So only in 1692 did Newton finally publish his work on fluxions. Okay. So for these derivatives, they were denoted as x dot, x double dot, x triple dot. These were how the derivatives were denoted. So this is if I have x as some positional function and t is the time parameter. This would be the derivative with respect to t. Instead of dx dt, for dx, he wrote this x dot o, and for dt, he wrote o. And so we know that x dot is dx dt, but this in his writing would be x dot o over o. So it's just x dot, right? Okay. His notation for integral was worse, but so in 1704, he published, this was in an appendix to a book on optics, an appendix to a book on optics that contained work on fluents. And these are integrals. Okay. So he showed the connection between what he called fluents and quadratures. Well, you might recognize that word previously. Quadrature is the word that Archimedes, this is the word that was used in the translations of Archimedes for area. And so he's talking about the connection between integrals and area under curves. That's definite integrals. So these are actually the two quantities. But this was only done in 1704. Okay. So in 1696, he abandoned his professorship and took up a position as master of the mint. Newton was Newton was not the nicest of guys. He was actually kind of an overall like terrible person to be around. Um, so there's a number of things about Newton that don't get as much attention. So when he took up this position as Master of the Mint, he went full force on his duty as Master of the Mint. And one of the duties that he had as Master of the Mint was um, combating counterfeiters. Okay. Um, and he took this so seriously that he personally would essentially engage in these entrapment uh, schemes where he would go to local taverns or local places with people and basically solicit in secret for someone to produce him counterfeit coins, and when they did, he would have them arrested and executed or horribly maimed or imprisoned. So Newton did this routinely. He was very serious about it. He also, I'm not exactly sure the exact period of his life that this occupied, but for the last, I'm not exactly sure when it started, but for the last many years of his life, like several decades, Newton didn't die until 1727. So I believe, no, 1727 is when Newton died. So for the last couple decades of his life, he devoted it to alchemy, right? And this was long after it was known that alchemy would never yield, gold from lead, right? Years after it was known that alchemy was not possible, Newton was highly interested in alchemy. So devoted most of the rest of his life to alchemy. Of course, it's funny because when someone is as high an achiever as Newton, we can definitely forgive those things, right? We care about their contributions to math. It doesn't necessarily require them to be a nice person or someone you'd want to have a beer with or something. So he definitely is allowed some not so great qualities. Okay, so we'll talk about Leibniz next time. I just wanted to close with a quote from Newton. So a couple of quotes. So one, I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore and diverting myself and now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. The other quote that is the name of that compilation book I'd mentioned, On the Shoulders of Giants, is if I've seen further, it's by standing on the shoulders of giants. So he was referring to all these mathematicians whose work he used a lot, right? I mean, he used Descartes. So he used Descartes a lot. He used Wallace's method in computing these areas that he wanted to find. So all of this work that he used relied on previous mathematicians. So it is definitely not inevitable that without the work of the previous mathematicians, Newton figures out all of this stuff, right? It might have taken him the same amount of time to figure out much less stuff. And so it's a good, nice, optimistic way. If you're just a single person wanting to make an impact on a field, it's a nice, optimistic way of thinking that, it's not everyone has to be a Newton. There has to be several people piecing things together, right? Like Wallace, how many people have heard of the name of Wallace before looking into all this, right? It's not a common name that gets tossed around, but his methods were used all over the place by Newton. Okay, so next we will discuss Leibniz. So Leibniz mathematically gave us a lot more than Newton because it is still his notation that we use. So for derivatives and integrals, we use Leibniz's notation. His working out of the infinitesimal calculus is basically A just slightly cleaned up and spruced up version of that is basically the calculus that is taught around the world as Calc 1 and Calc 2. Um, so, and Leibniz was the first to publish his work on differential and integral calculus. He published it before Newton by a few years. And so both of them, discovered this kind of independently, and so they both get credit for the discovery of calculus. But in terms of impact on notation and current way that calculus is taught, Leibniz is definitely the bigger contributor to that. So anyway, we'll talk more about that next time. And then we are rounding up our discussion of the 17th century. We're going to get into 18th century mathematicians. And after, the problem is, even in the discussion of 18th century mathematicians, things are getting a little complicated to kind of keep going at it from a generalist perspective. Why did Newton wait so long? That's a good question, and I'm not sure anyone really knows why Newton waited so long to publish. It is clear that he could have vastly simplified Principia Mathematica by using calculus, right, that he invented in Principia Mathematica. I was actually shocked years ago. So I picked up a copy of Principia Mathematica. It was it was before my freshman year of college, so it was right after I got out of high school. And, I knew that at that point that Newton and Leibniz had discovered calculus. And then when I tried to read Principia Mathematica, I was like, where's the calculus? I don't see any derivatives here. And it's because there wasn't technically. All of the argumentation used is not... Principia Mathematica could have been cleaned up substantially if Newton had used infinitesimal calculus instead. And it's clear that he didn't do it because he was worried that it wouldn't have been as widely accepted. People would have questioned, like, where did this come from? Like, we don't believe that this works. And so it could have just been as simple as that. It's like he believed in his heart that it worked and it got these results. He couldn't prove that it worked, I guess. Or he couldn't. I guess he felt like he had justified it to himself, but that maybe others wouldn't view it as proper justification. And infinitesimal calculus wasn't really on 100% solid footing until much further, like the late 1800s. And so this was something that mathematicians at the time, even later, even by the time of Euler, who lived many years after Newton, or did most of his math work years after Newton had died, Euler basically himself used a bunch of arguments that were not that rigorous because the whole field wasn't rigorous enough until much, much later. But they were still able to do all these amazing things because they were correct. Their reasoning just wasn't 100% spot on. And it could just be, that he had these reservations. But for whatever reason, he published his results after Leibniz had already published his work on derivatives and integrals. So that's how it is. But it's clear that both of them discovered it independently, and so they both get credit. And even if there's some question about Leibniz discovering it independently, just the fact that the way that he did it, the notation that he used, is still what is used all over. It's the universal notation. That alone has a huge impact. But anyway. As we pass through the 18th century mathematicians, going at it from a generalist perspective is going to start being a little bit too hard. And so I'm going to put out a poll to basically see what direction you all want to go in after this, because it will be kind of too hard to give you a snapshot of everything, because it's an absolute explosion. Too much stuff is going on. So I'll let you all know about that. Anyway, I will see you all on Wednesday.